All right, so what we're going to do today is we're going to start our discussion of statics and torque. This is chapter 9 in your book. I noticed a minute ago that I had uploaded the wrong slide, so sorry about that. That's fixed in Blackboard now. So you should have this under your chapter 9 notes. Everything that we've done up to this point, we've been looking at basically just applying forces, right? We've been doing a lot of free body diagrams, and we've been looking at motion in multiple dimensions. We've looked at it from the standpoint of applied forces. We've looked at it from the standpoint of energy. We've looked at rotational. We've looked at linear. We've combined them in some cases. What we're going to start thinking about now is these forces exist on the objects, regardless of whether they're really in motion or not. Generally, when things are not in motion, that's what we're going to look at. And that's the idea of statics. So if you think of the word static, meaning to be still, that's what we're talking about. It's things that are being still. So we'll just go through some slides here and talk about it. Come on, assuming PowerPoint will cooperate with me. All right, so this is a pretty interesting picture here. So we have some rocks out in some national park somewhere. Now you'll notice what's interesting is particularly up here in the top right of this picture, we have a bunch of rocks. It looks like kind of a stone mushroom or something. And these rocks seem to be kind of balanced on each other. Now, clearly, these rocks have weight, much more weight than you could ever lift without some kind of machinery or something. So there must be a weight force. But you'll notice this thing is not moving. So there are forces, but they're in what's called static equilibrium. And if we were to look at a static equilibrium problem, we see that this is kind of what we've already done, right? So we have some mass, this person, and they have weight. So here's the vector. They had normal force. This is the ground pushes back on the guy. Notice in this case that we've drawn the normal force vector coming from the ground, from center of the earth. But when we do our free body diagram, we generally do it like this with the tail of the vectors together. It doesn't matter how you draw this. I generally go with the free body diagram because this lets me determine very quickly if my system is in equilibrium or not. This case is in equilibrium because there's no motion. We're assuming the sky is not oscillating up and down. We're not moving left to right. So what we can say when the system is in equilibrium, that the sum of those forces or the net force on the sky is zero. And we can prove that pretty easily. We know that our weight is just our mass times the acceleration due to gravity. And we know that our normal force is whatever that frictional force between the two is. And actually our normal force, the frictional force would be mu n, coefficient of friction times the normal force. The normal force here is going to be exactly the opposite of the weight force. Now, because there's not an incline here, we don't have to worry about sines, cosines, anything like that. But because this guy is not moving in this direction, that means that the weight force must equal the normal force. Thus, we say the system is in static equilibrium. Well, what about this situation? Here we have a car, and the car is moving. It's moving to the right here at a constant velocity. So if we were to go and draw a free body diagram here, what's going on? So obviously we have the weight force of the car. Now, the weight force of the car obviously is just a function of its mass and the acceleration due to gravity. Notice that we have 4 normal forces labeled. Well, this represents the 4 tires on the car. And notice in our free body diagram and over here, we've drawn these vectors to be a little bit shorter to indicate that that amount of force is not as great as the total weight. What we should find here, if this is to scale, is you should find that each of these normal forces is 1/4 of the weight force. Thus, again, the normal forces, and we're talking about some of the forces, not just one of these. This is net force. So the sum of the normal forces has got to equal the weight force in this case, because there's nothing else going on. So the net force in the XY direction is going to be 0. But let's look what's happening in the Y direction. The car is certainly moving. We have a constant velocity. We have some applied force. So this is going to be the force that comes from the motor turns the crankshaft, which turns the axle, which causes the wheel to rotate. We get an applied force between the wheel and the road. So this is what our kind of pushing force is that's making the car move. We also have a frictional force, this lowercase f. Remember, that's our mu n. Now, this car is not oscillating back and forth, right? But it is moving forward. But here's the trick. Because we have defined this as a constant velocity, that means that the rate of change of velocity, right, over time is going to be 0 because it's constant, right? Think about the speed of the vehicle whenever we start measuring is 60 miles an hour. And then we measure it again 10 seconds later, and it's still 60 miles an hour. And we measure it again 20 seconds later, and it's still 60 miles an hour. So in that case, if we wanted to look at the change in velocity over time, we'd look at our delta V. So our final minus initial, in the case, both of those would be 60. So our delta V would be 0, and our time might be 10 seconds. So our delta V over T goes to 0 because it's constant velocity. Well, you should recall that delta V over T is acceleration. So the acceleration in this case is 0. Remember, force, net force, has got to be equal to 0, but Newton's second law tells us that this net force is always going to be the mass of the system times the acceleration of the system. Well, if the velocity is constant, that means there is no acceleration. So ma is just mass of the car times a's acceleration is 0. So F must go to 0 because m times 0 is 0. So there is no net force because there's no acceleration. But what that means, since there's no acceleration and the net force is 0, the only way that's going to happen in the y-axis is if the applied force is equal to the frictional force. So this is what's called dynamic equilibrium. So don't get tricked by the equilibrium stuff into thinking equilibrium means necessarily no motion. What it really means is there's no acceleration. So there can be motion, right? There's just not going to be acceleration. In this case, the car is certainly moving, but it's not accelerating. So the velocity is constant. So here's another example, a little bit different. So we have this hockey stick, and let's say it's laying flat on the ice. Okay, we're looking down on the top of this thing. It's just laying on the ice. And we come along and we apply two forces, one from the right side, one from the left side. And let's say that those forces are equal. So it doesn't really matter what the shape of this thing is. It doesn't really matter where we apply these forces, because our free body diagram tells us that these two forces are equal and opposite. Since it remains stationary, there is no net force, right? Why would the net force be 0? Because this should be labeled F1 and this be labeled F2. They have to be equal, but they're going to have different signs, right? So if you sum them, you get F plus or minus F, or F minus F, and that should give you 0. So we know we're not going anywhere. So this is our static equilibrium. Now, in this case, we're talking about this hockey stick on ice. We're going to assume that there is negligible friction here. But what happens if we come along and we apply a force, but these forces are not going to be parallel to each other? They're going to be the same in magnitude. So we've got these two opposing forces of the same magnitude. So the net force has got to be 0. However, if we do this and we're off center here, then this thing is going to rotate. So we get our net force F has got to be 0. But it's not at equilibrium because it's moving. So it says here the net force 0 is a necessary but not sufficient condition for achieving equilibrium. So what that means is that just because the forces are equal doesn't necessarily itself imply an equilibrium. There's something else going on. Well, that something else going on is torque. Because remember, we're talking about net forces. So in order for this to be true, there must be no other force, right? These forces are equal and opposite. There's no other force. In this case, they're equal, they're opposite in direction, but they're offset from each other along some other arbitrary axis. And suddenly we get movement. So even though the applied forces sum together to 0, there's movement. That implies that there's still an acceleration, right? Well, because we're talking about net forces, that means that these two forces are not the only thing going on here. There's another hidden force that we haven't considered yet. And it comes from the fact that these are offset. And this force is called torque. So here's a couple of examples. So let's say that we're looking at a door. And let's say we're looking top down on the door. So here's the doorknob, here's the top of the door. We know that the distance from the hinge out to the doorknob, that's going to be given to us by some R. We're going to call this R perpendicular. So our perpendicular radius, this is called our pivot arm sometimes. Our perpendicular radius. And then look what we're doing with the force. Here's why we call it R perpendicular, because it's the radius that is perpendicular to the applied force. So it's always in 90 degrees there, right? So we apply that force. If we go the other way, that's just a negative force, not a big deal. So look what happens as we start playing with where this vector is. So here's our perpendicular. But if we notice that we draw some triangle here, notice how useful triangles are. So here we draw some triangle, but we can tell for sure that depending on how far this door is open, we have some angle. Okay, it's this angle theta. Remember we talked about R perpendicular. That is the radius as measured that is perpendicular to the force. But that's not exactly what we need, right? Because really what we want is we want to look at this force as it relates to the hinge. So this is a much different distance. So the reason we call this a radius is because you can imagine that if we continued pushing on the door with our perpendicular force, if this wall wasn't here, this would just swing in a circle, right? So anytime we see R and theta, we're talking about circular motion. So we're going to start swinging the door. So where we push on the door is certainly going to matter, right? So you can try this experiment at home. If you try to open the door and we push the door or pull the door, however you like, and you do this out where the doorknob is, this is pretty easy. The closer you move in towards the hinge, this gets pretty hard, right? Especially if you have big, giant, heavy wooden doors like I have in my office. This gets difficult to do. Also, that's if you're applying that force directly perpendicular. Well, what if you're not applying the force perpendicular? Well, then we need to know that piece of the force that would be perpendicular. So that's where we use our trig, right? So we're looking for this force. So we get R perpendicular equals R sine theta. And so we'll notice that this gets harder to do still if we're applying at this angle. What if we apply the force directly along the radius? Then our R perpendicular goes to 0. Now, clearly, the door is not going to move, right? Because it's anchored here and we're not going to move left and right. So here we have this force is 0. So what we're really looking at here is this force, this kind of perpendicular force, this force that's dependent on this R perpendicular. We're going to call that torque. So torque is kind of our rotational force. This is the principle that screwdrivers work on, right? If you need to screw something in with a screwdriver, then typically you'll notice that the longer the screwdriver is, the easier it is to do. If you do a lot of mechanical work like I do and like I did on airplanes, you'll find that a lot of times you'll encounter places where you just can't get to the thing with a long-handled screwdriver. You have to use a short one, and it's very, very difficult to do because you have to turn a lot harder. So this is your idea of torque. So we know that that force, that torque force, has got to be dependent on a couple of things, right? It's got to be dependent on how hard I'm pushing against the pivot point. So this perpendicular force here. And it's got to be dependent on whatever this R perpendicular is, right? Even if we apply it at some angle, we can still derive what that R perpendicular is as a function of that angle. So we know that our torque has to be related to this force and this distance. In fact, this is not just a standard multiplication when we do this. This is actually what's called a cross product in calculus. So we say that our torque is R cross F, or R perpendicular times F, if you like. So our R cross F, that gives us our torque. A lot of times you'll see torque represented by the Greek letter tau. So let's look at the hockey stick example again. So here we have our hockey stick, but this time we've put a nail. So we've anchored this thing. And we're now going to come along and we're going to apply a force. Well, notice because of the way that this hockey stick is angled, we have to kind of imagine this perpendicular R here, right? Because we want the force to be perpendicular to it. And that's what we need to find the torque. So we need to measure this angle. So we need our perpendicular. Remember, our perpendicular is generally r sine theta. So we could measure this distance r between the force and the nail, multiply that by the sine of this angle, and we get our perpendicular. This is exactly the same thing that we did with the push the box up the hill problem, right? We just found component vectors. This is exactly the same thing. We're not doing anything new here, except that we're going to use that component vector in a little bit different way. In this case, we do the same kind of thing. Here's our nail. Here's our force. But look what we did. We put the nail up here so that our R perpendicular is maximized. Putting the nail down here, we've got this angle. So this is going to be a little bit different, right, in the force that's generated. We've probably all done this thing. So this is your seesaw thing out on the playground. So what we've got is our pivot point here. And we have some force, this pivot force, or this perpendicular force here. It's got to be pointing this way. Now, in order for the seesaw to be balanced, what do? Well, again, if it's balanced, then that means that the sum of our forces have got to be zero. And the force that we're interested in is we want to balance this kind of upward perpendicular force. So we have two kids on here of mass 1 and mass 2, and they each have different weights. So intentionally, they've drawn this girl on the right to be significantly larger. And if you'll notice, you can tell just by the diagram that she has to sit much closer to the pivot point, whereas this kid has to sit further away. Now, the reason for this is because these two weights are different. So if they sat at the same distance, you remember you would then have to worry about your perpendicular force. You'd have to worry about torque. In order for the system to be in equilibrium, all the forces have to be equal, not just the weight forces and the normal forces. Well, there's that other hidden force, right? Because we've got an offset here, and that's our torque. So our torque on the right side here would be W2 times R2, because that's clearly perpendicular. And on the left, it would have to be W1 times R1. So that would be two torques. So the weight force on the left plus the torque force on the left has got to equal weight force plus the torque force on the right. And in order for this to be in equilibrium, all those have to equal this perpendicular force. This is a very odd diagram. For some reason, we have this guy with a doll in his hand, and he's trying to balance it. Now, notice what we've done here is that with this pose, we've marked different centers of gravity for different parts of the doll. And what we're interested in is making this force perpendicular between where the guy's holding it and the total center of gravity. We want that to be perpendicular to balance, right? So you can see what happens as we add weight to one side or the other, as we change this angle, then this thing wants to fall. So we've got to keep those forces aligned in order for this to be in equilibrium. If we don't, there's going to be motion, which means the doll's going to fall over. So let's say that we need to talk about these kind of different equilibriums, right? So in this case, we've got this pencil and it's in static equilibrium. So the net force on the pencil is 0 and the total torque around any pivot is 0. So not spinning, not moving up and down, not moving left and right. Here's that Greek symbol tau I was talking about. That's our torque. So tau's got to be 0. Here's our free body diagram of forces. Since tau is 0, we're not putting them in there. If we had taus, then they would be represented by arcs, right? Because it's rotational motion. So it's not going anywhere. It's in a static equilibrium. What about this? If we displace the pencil slightly, so we rotate it a little bit, so we change our pivot point, it's no longer in equilibrium, right? Because we now have a weight force that's offset from the normal force. So there is going to be some angle theta there, right? So if we find our perpendicular component of the weight force, it's going to be the distance times the sine of that offset angle. So that's going to be our tau. So this is tau sub CW, so clockwise torque is all they're saying here. So since this is displaced, we're no longer in equilibrium. This is an important concept here. The weight produces a clockwise torque, sure, right? Because the weight's going to want to force this pencil down in the clockwise direction. And what it's doing is it wants to go to equilibrium, right? It wants to be stable again. And it wants to do that with the least amount of energy as possible, right? Because just like we talked about before in conservation of energy, we want to minimize energy transfer. So nature tends to go from high energy states to low energy states by the shortest route possible. Now let's pretend that we had the ability to rotate this pencil 360 degrees. Well, it still requires a whole lot more force to come around all the way counterclockwise before we get back to the equilibrium position than it does for the weight vector to just pull it down. Eventually, this thing's going to settle out into its equilibrium position. But what happens if we go too far? Look what's happening here. So with this small pivot, our center of gravity is to the right of our normal force. And so our weight vector wants to pull down. So we're going to pull back towards equilibrium because it's in the opposite direction of what our torque force is. But look what happens when our center of gravity passes our pivot point. If our torque vector in the counterclockwise direction then takes over because this weight is shifted, then our torque force goes counterclockwise. It can no longer go back to equilibrium. So the displacement is going to continue to increase. Well, if this displacement is continuing to increase, that means we have change of velocity, we have an acceleration, therefore there's a force. Now the torque is significant. What if we do this? So this is what we call a stable equilibrium, right? Because as soon as we go off of this position, this wants to settle back down to a state of equilibrium, and it wants to do the shortest path possible. This is called an unstable equilibrium. So our torques are equal, our weight and our normal force are equal and opposite, but we have a very small pivot point. So you can see that it doesn't take much for this center of gravity to be displaced well beyond the pivot point in either side. So if we displace even slightly, we get a torque created by the weight that's in the same direction as the displacement. So if we make a displacement in either direction, we're going to get motion. We're going to go against, we're actually going to make our torque force take over. So we're going against equilibrium. So that's what's called an unstable equilibrium. you could certainly, given enough time and patience, you could certainly balance a pencil like that. It would be extremely difficult, but you could do it. But as soon as a slight breeze comes along, the pencil's going to fall over. You balance a pencil like this on the larger flat end, where now there's a lot more room for this shifting, so that you don't overcome your torque. It will come back to rest. That's what's called a stable equilibrium. There is a much, much more complicated mathematical way to do this that's outside the scope of this course, but it's extremely useful because, as everything else in this class, this is a pretty simplified example of balancing forces. In real life, there obviously are there are many more forces that we have to worry about. One of the places that we use this in quite a lot is orbital dynamics. When we talk about satellites and things, we want to put satellites in orbits. Orbits are nothing more than equilibrium points, where the rotational force is equal to or greater than the weight force. And so that's all you're doing in an orbit, is you're constantly falling in a circle. So you're falling at the Earth and missing. There are places, if you do the satellite problem, and I may show you this in the next lecture, if you look at a three-body problem in orbital dynamics. So let's say we have a system with the Earth, the moon, and a satellite of some kind. You can easily calculate the force due to gravity on that satellite because of the moon and because of the Earth. And I think I've showed you this briefly before, how you can calculate gravitational potential as GMM over R squared, inverse square law. So we'd set those equal to each other. And we'll find that there is some distance at which the force of the moon on that satellite is equal to the force of the Earth on that satellite. These are called Lagrange points, and they're extraordinarily useful for making orbits of satellites and things. For example, the James Webb Telescope that we launched last summer is actually out at a Lagrange point. It actually orbits a Lagrange point out well beyond the moon at L2. L2 is a stable Lagrange point. There are other Lagrange points, I think it's 5 and 6, are unstable Lagrange points, where you get this problem of it doesn't take much of a perturbation of that orbit to throw this equilibrium out. And so the thing will spiral towards one object or the other. So that's an unstable equilibrium point. And we generally don't use those because they're unstable. But my point is that this is all about summing the forces. That's all we're doing. So here we have a neutral equilibrium. We've got some sphere, and we've got some pivot point. So we have this sphere, and we can displace this thing. Now, because it's a sphere, that weight vector is always going to be perpendicular to the normal. So that thing is going to be pretty stable. Same thing goes on here. If we look at this pencil, this is just looking at from the back, this is looking at from the side. So we're still in an equilibrium point here. So another free body diagram. So we've got somebody standing here, and we've got a pretty wide stance. Here's our free body diagram. Here's our center of gravity. So what we can do here, you'll see this in things like skateboarding, skiing, snowboarding, things like that. If you tend to do this squat and widen your stance here, because of this distance, what we're doing is, notice that we have normal forces on each foot. So they've got to be perpendicular to this distance between the weight vector and the normal force. So this is why by lowering your center of gravity and widening your stance, you're more stable. Sumo wrestlers do this. If you ever watch sumo wrestler, they tend to take this very low, wide stance, right? Because the whole point of sumo is to stay stationary and stay inside the circle. So you'll always see sumo wrestlers get that low, wide stance. That's because they're trying to make their equilibrium as stable as possible. So the taller you stand and the closer your feet are together, you're less stable. And you can try this at home too, right? This is why try standing on one foot is a little more difficult, right? Because that center of gravity shifting, you got a little bit more weight on one side, because your normal force is not going to be aligned with your center of gravity. It's going to be really hard to do, unless you're a flamingo. Take a look at a flamingo. When they stand on one foot, you'll notice that their one foot tends to be directly underneath their CG and they don't wobble around a lot. It's because their physiology is made for that. This is another odd diagram that's in your book about the same thing. So chickens have these really high pivot points on their waist. So they're pretty stable. And this says the body of the chicken supported from above by the hips and acts like a pendulum. So this is why chickens kind of walk the way they do. I'm curious if this is the same chicken that we slapped to cook the other day. And then we get into more examples like this. So I think that's where I'm going to stop today. In the next lecture, what I'm going to do is I'm going to work through a few examples that we're going to apply this. And we're going to do things like determine how much torque you need to apply to cause something to rotate. Where does this weightlifter have to hold the bar in order to balance the weight, and do some things like that. We're also going to start talking a little bit about a whole field of study. If you take an engineering course, you can take a course in statics. It's basically about building bridges. And we'll take a look at some bridge problems where you have suspension bridge. You've probably all seen these things and they have a lot of structure above or below them. There's a couple of games that you can go play online that are free. They're about building bridges. And we'll start to examine that structure and how we use static and some of the forces to make stable platforms and stable bridges. And just continuing to apply this. So that's the plan. In the next lecture, we'll do a bunch of examples about that. There will not be a live lecture on Friday because I'm going out of town, but I will be recording a lecture prior to that. I will also be recording 3 or 4 different lectures that will be posted on the channel and give you a homework assignment that will be due over the week that I'm gone. So we won't lose any time. And then when I come back, we'll have about 3 weeks left in the semester and be done with this. So as always, if you need help, come ask. Otherwise, just keep doing what you're doing. And I will see you guys in the next lecture.